Morning, guys. Hopefully everybody's doing all right. If you could give me a green check mark, just make sure everything's going smoothly, and we'll get started. Welcome, Kayla. This is first science class. Kayla's new to the program, and hopefully foods and PE went okay with you with Mrs. Wood this morning. What I wanted to talk about today was we were talking about energy flow and ecosystems last day, and we kind of almost finished it. I think there was maybe 1 or 2 slides left that I didn't get to, so we'll polish that off. We're going to talk about 2.2, which is nutrient cycles, and then we will kind of wrap it up there. There's a few people who haven't given me green check marks. Is everything kind of going okay here, or what's going on? There we go. Sleep at the wheel. Okay, so last week we finished up Unit 1. There were sort of 4 things in Unit 1. We did the climatograph, then we did the create a creature assignment. You have the Unit 1 learning guide, and you have your Unit 1 test. So I just went in and had a look at the climatograph. Say about 3/4 of you have submitted that. About half of you have submitted the create a creature. And then the Unit 1 learning guide, I think I only had 4 or 5 submissions. So you guys, I know you have more than just this class. You also have, socials and foods and PE going on. But it's really important that you stay current with the material. So if you start getting behind in the very first unit, you're digging yourself a huge hole. So it's not too late. You guys have an opportunity here to, get caught up and get back to current. I get the impression that a few of you guys are kind of trying to do it all at the, the end of the unit, just trying to get everything in. And then it's just overwhelming. I can't tell you how to do your stuff, but don't leave it all to the very end and just try to do it all in like a couple of days. Just take a small piece, one section. We just did 2.1 last day. Do it a section at a time, and then you won't get overwhelmed with it. And if you do run into problems, then you'll just be able to, ask in class. So thanks, Kaylin. Scanning and getting in is half the battle. Some of you guys probably have some of the work done, you just haven't submitted it. I can't mark what I don't have, so that makes things a little bit difficult for me. So for some of you, you haven't submitted anything yet. I don't even know if you're participating in the course. I mean, I see your names in chat, but it's kind of important that you guys try to stay current because we keep moving. There's a ton of material to cover, and we just keep cruising. Whether you're with us or not, we'll keep going. So we're about midway. Today will be the midway point of Unit 2. That means we'll be done Unit 2. I believe we have class on Thursday. I think we have a double block on Thursday morning. So you guys will have you'll have Unit 2 stuff due then too. So it's gonna catch up to you, and I don't want you guys to get behind at the beginning. So you need to dedicate some time to getting your science done, and just keep chipping away at it a little at a time. All right, so that said, for those of you who are submitting work and getting things done, awesome possum, thank you, I appreciate it. Some of you have submitted your Unit 1 learning guide. Once you submit your Unit 1 learning guide, I'll just go through it. It's really not a ton of stuff in there. I think there's only like 4 pages where you actually aren't just filling in notes. So I go through it, I look at it, I make sure everything's good, make sure there's no obvious errors, and then I will send the test password to your whoever your parent contact is on file, and whoever's looking after you, and then they are to supervise your exam. So they just basically watch and make sure that you're not looking at your notes and things like that. So all of our exams in science are closed book, and we'll do 2 midterms, middle and end, just like we did in math. So that's kind of where we're at. Unit 1 was due the beginning of this week. I think I asked you guys to finish it up for Monday, and then your test should be done, today or tomorrow sort of thing, because on Thursday you're going to be done Unit 2, and then you're going to have to submit your Unit 2 learning guide, and then you're going to have a Unit 2 test to write. I mean, the tests aren't long, but the unit learning guides are long, so enough of me talking. We went through all of this stuff last day, and the important thing here is that you recognize that we talked about the different types of animals: carnivore, omnivore, herbivores. When we talk about food webs, it shows multiple interactions. We talked about keystone species. The energy flow is kind of the big idea here. So this always comes up. You'll see it on your test. You'll see it on your final exam. Energy is lost from each level. As you go up a food chain, energy is lost. Where does it get lost to? We talked about it last day. So if I'm a plant, I grow. I don't need to move. I don't need to do anything. I just grow. I get energy from the sun. I don't have to move. I don't have to obtain energy. Now, if I'm a grasshopper, I want to eat the grass, the plant. Now I got to move to the grass to get it and eat it, to get my energy. I don't get energy from the sun just by existing. So when we go from one step in the food chain to the next step, we lose 90% of the energy. So the energy from the sun gets transferred to your producers. Let's say those producers take in 10,000 joules of energy. You are only passing on 1,000 joules to the next level. And then the same is true for that transfer. So if you go from your primary consumers to your secondary consumers, you've gone from 1,000 down to 100. And then you go from 100 to 10. So by the time you make it to the top of the food chain, you started with 10,000 joules of energy, and you're left literally with 10. You lose 90% of the energy at each step. 10% is transferred. It's a super important idea. You'll definitely see it again. I can't stress that one enough. Where does the energy go? We looked at this diagram. We talked about it a bit last day. So the higher you are in the food chain, the more work you need to do to survive. If you are a grasshopper, you just got to go find the food. If you're a mouse trying to eat a grasshopper, first you got to go find the grasshopper. Then you got to eat the grasshopper. That takes energy. You got to, reproduce. That takes energy. You got to build a home. That takes energy. So the higher you go up the food chain, the more energy the organism expends on just surviving. At the very bottom of the food chain, a plant doesn't expend energy searching for food. It doesn't expend energy doing anything like that. So that's the important idea here. That's a food pyramid. Shows you how much energy is lost. And this is the rule of 10. 10% passes to the next level. That means 90% is lost at each trophic level. You'll see different pyramids showing different things. So you can see pyramids of energy. You'll see pyramids of biomass. So as you go higher up a food chain, the number of organisms gets smaller. And pyramid of numbers, the last one, shows you that if you have 1.5 million primary producers, then you go to the primary consumers, you're 200,000. Secondary consumers, you're 90,000. Tertiary consumers or third level consumers are much smaller again. So higher you go up food chains, less energy available, less organisms, less biomass. That's why it's a pyramid. Higher you go, smaller it gets. And that was the end of 2.1, so energy flow. Does anybody have any questions about anything in there from last day? Should mention for Kyla and maybe Kira's been here a few times. In the course, Science 10, at the top of each unit, there is a learning guide. And that's what you've printed off here. We're just going to go through the learning guide kind of page by page. And you can fill in the notes as we go. So we've gone from energy flow in ecosystems. Now we're into nutrient cycles in ecosystems. Now, for today's nutrient cycle stuff, I tried before class to flip this, but it didn't work very well. So at the very top of the course in Moodle, you have your data book. And today's actually the first day where, well, I shouldn't say that, there's some biome stuff in here. But today's the first day where the data book is going to become really, really important. So if you have a data book printed off, you might want to pull it out. We're not going to use the periodic table, we're not going to use the pH scale, we're not going to use any of the nutrient or the atoms, none of that stuff. Oops. But we're going to start on page, what is this? Data page 8, hard to see. So pages 8, 9, and 10, and 11. This is all the biology stuff. So we're going to go through these diagrams today, and we're going to talk a little bit about them. The good news is for this section, it gets kind of complicated, but there are these nutrient cycles in your data book. So you don't have to memorize any of this stuff. You just have to be able to find it in your data book. That's one really good thing about the biology unit in Science 10, is that you are basically just referencing the data book for a lot of it. So I'd say on your final exam, probably 10% of your final exam, or 10% of the course, is just referencing your data booklet, not needing to know much more than just where to find some stuff. And I didn't mention it yet, but on page 10 in your data book, you get this map of all the biomes. I tried to flip it sideways, it didn't work, so anyways. Mr. Ross to the rescue, look at that. So all the biomes are there, color-coded, and you'll be able to access the biomes. So you don't have to memorize the biomes, all 8 of them, they're given to you in there. And the nutrient cycles we'll look at a little bit more closely right now. So I'm just going to jump back into section 2.2. So this is the second section of chapter 2, unit 2 in your notes. This is nutrient cycles, and this section, you need your data booklet. And all of the quizzes and tests you write, you can use your data booklet. And a lot of the questions from this chapter are just accessing information out of your data booklet, which is really good. So nutrients are chemicals required for growth and other life processes. Nutrients move through the ecosystem in cycles. So nutrients aren't just magically created and they don't disappear when we're done with them. They just cycle through. And that's kind of the important idea here. Nutrients often accumulate in areas called stores. So we have 2 different meanings of the word store. If I go to a store, what is it? Well, it's a collection of things. If I go to the electronics store, it has a bunch of electronics. If I go to the grocery store, it has groceries, it has food. I could go to all these stores. So the word store means to literally store things. A bunch of things are located there. So in science, when we talk about stores, we're talking about places where usually nutrients accumulate. Without interference, kind of the big theme of Science 10 biology unit, without interference, generally the amount of nutrients flowing into a store equals the amount of nutrients flowing out. So if humans weren't here, nutrients entering an area is the same as the nutrients leaving, and we go and wreck things. So if you've ever gone to a gardening store, bought fertilizer for plants or whatnot, you'd likely seen on the front of the package, it'll always have 3 numbers, 18, 24, 6. Different fertilizers will have different combinations of numbers. Some are for building roots, some are for different types of plants. But the 3 numbers always represent nitrogen, phosphorus, and potassium. And you get different numbers depending on if it's for grass or for your vegetables or things like that. Different plants require different levels of nutrients. So the 3 nutrients, nitrogen, phosphorus, and potassium, are important to life. That's what's on fertilizer. And we're going to look at a few of these a little bit more in depth. So obviously human activities can upset the balance of nutrient cycles. We cut down land for agriculture, growing crops or cattle, things like that. Mining, if we look at the oil sands in Alberta or this big open pit mine here, we're literally scraping the forest off the top of the earth, the surface, and we're digging, and we, need the whatever's under the ground for whatever reason. Excess nutrients in the biosphere can have unexpected consequences. Now, there's a picture behind me of this green. This is the border between two countries. And does anybody know where this is? So obviously different sets of laws here and here. Anyone imagine where this might be? Jonah, do you know where this is? Jonah, could you take a guess as to where this is? Jonah, I'm going to lean on you right now. Jonah, what is this picture of? Jonah, this is the border between a little island in the Caribbean. On the left is one country, on the right is another country. Country's kind of on an island, split in half, pretty much down the middle. Come on, Jonah. North Korea. Oh my goodness. This is the border between Haiti and the Dominican Republic. So on the left, Haiti, you can see they've pretty much clear-cut all of their forests. And then in the Dominican Republic, they have different laws regarding forestry and land use and things like that. North Korea would have been a good guess. Thank you, Jonah. There's no trees there in Haiti. This is the first time I've ever shown this picture where actually somebody is there and you didn't even know. No trees in Haiti. Trees are a resource, right? People have a desire to cut down trees to build houses, furniture, things like that. But if the government isn't able to, control the amount of trees that are cut, people will just cut down all the trees and there'll be nothing left. It's kind of like the Lorax. I read that book to my son a lot. Jesse, North Korea border kind of looks the same just because of the DMZ, the demilitarized zone. But in Korea, there's trees and stuff there, North Korea and South. All right. So the 5 main chemicals essential for life are C, carbon, H, hydrogen, O, oxygen, N, nitrogen, and P, phosphorus. Nutrient cycles for carbon, hydrogen, oxygen, and nitrogen are all in the atmosphere. And then we talk about phosphorus is actually has to do with like rocks and things like that. So we'll look at those in a second. Elements, carbon dioxide, water vapor, oxygen gas, nitrogen gas, traces of NH3 is ammonia, NO, nitrate. Phosphorus cycle does not include the atmosphere, and the main source for phosphorus is out of rock. So we'll look at how we get phosphorus in our diets. First one we're going to look at is the carbon cycle. Now, you have a page in your data booklet that talks about the carbon cycle that looks a little bit different than this. But it's the same idea. This is the carbon cycle. So everything that we are in terms of our bodies, our construction, we're mainly made of water and carbon. It's kind of the building block for life on Earth. If you're alive on Earth, you're a carbon-based life form. So carbon's extremely important for all life on Earth, plants, animals. The basis of our structure that we are, what we are made of is carbon. Carbon's really an important atom. We'll talk about it when we get into chemistry, but carbon forms 4 bonds. There's lots of carbon on Earth. That's why we're probably made of carbon. And we need to look at how carbon kind of gets cycled, but we know a little bit about carbon already. We've talked about photosynthesis, where you take carbon dioxide out of the atmosphere, you turn it into a plant, and then that plant kind of gets eaten, passed on, sort of thing. So we've talked about carbon dioxide being captured by a plant, and then we talked about cellular respiration is how we access that carbon. So normally a plant will take the carbon out of the atmosphere, turn it into a sugar, we eat the sugar, turn it into ATP, that's energy for our cells. So it's important to know what's going on in this image. You don't have to memorize anything, of course, because it's given to you, but you need to know how to understand it. And at first glance, it's a little bit tricky to get, but we'll see if we can figure it out. So there's a little a legend down in the bottom here. It says carbon cycle key. So anytime you have a number in a box, that's a carbon store in gigatons. Gigatons is like a gigabyte. It's like 1,000,000 bytes, so 1,000,000 tons is a gigaton. And when we talk about some of the big numbers, like very bottom right corner here, marine sediments and sedimentary rock is 100 million gigatons. It's very, 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 very large amounts. Does anyone else hear me, or is it just Kayla? She's typing in chat, she can't hear. Maybe Kayla is just in chat. We can hear you but can't see you? Oh my goodness. Oh, maybe because the image is up right now. Is that what you're talking about? See if we can get Kayla sorted out. Let's see if I can maybe get the link for Kayla. And ooh, I heard a ding. All right, sorry, just jumping around. All right, I think that should help her out. I'm going to continue. So the image, anytime there's a box, that's carbon being stored. If you have something in a circle, like an oval I should say, not really quite circular, that's an exchange of carbon. So if you have an arrow going up, that's carbon being released. You have an arrow going down, that's carbon, being stored. And then you have all of the different interactions showing that these arrows. So you have something like photosynthesis here, which is taking carbon out of the atmosphere and being absorbed by plants. Now, plants are generalized by this one tree, but this is all the plants in all of the world, absorbing carbon through photosynthesis. And then there's an arrow showing an animal like a deer. A deer eats the plant. Don't take it literally. This deer isn't necessarily eating this kind of sprucey pine tree. It's just a generalization. The deer eats the plant. You see the arrow goes from the plant to the deer. And then the deer breathes. And when he exhales or she exhales, this guy has some antlers, so when he exhales, the carbon goes back into the atmosphere. So you could talk about just this cycle here on the side where carbon gets exhaled through an animal and gets reabsorbed through a plant, and just this one sort of part of this cycle. Now the deer gets eaten by other animals. It's showing here the relationship here. The bear eats the wolf. So the carbon goes from something like a tree into a chipmunk, into a wolf, into a bear, and then the bear exhales and that carbon goes back into the atmosphere. So that's kind of one way it can go. Another way is the animal dies and the carbon goes back into kind of the soil, and then you get something like a plant absorbs the carbon, or the carbon decomposes back into the atmosphere, and you can cycle carbon that way. So it's showing kind of the interaction between plants and animals. Then you have these other sort of images here. In the background, you have a volcano releasing carbon dioxide. That's a major, major source of carbon dioxide. Volcanic activity, huge source of carbon dioxide into the atmosphere. And then you have things like fossil fuel combustion, where we burn fossil fuels. And this is kind of a big deal because this is the only one in this whole diagram that doesn't have an arrow going back down. We're just releasing carbon into the atmosphere and nothing counteracts it. It's not a natural process. So plant growth, absorbs 61 and releases 60, and that number is in gigatons per year. You have sea surface exchange. The ocean releases 90, absorbs 92 gigatons. You have these deep circulation ocean currents. Down here it releases 100, absorbs 92. Marine life absorbs 50, absorbs 40, releases 50. So this sort of image shows the interactions between all of the cycles. It shows how carbon is entering the atmosphere, how it's getting pulled out of the atmosphere, how carbon is entering rocks, how it gets pulled out of rocks. It shows interactions between animals and plants. There's a lot of information here, and there's a lot of numbers, and you just got to look at the legend and figure out what it's talking about, and then you'd be able to kind of translate that into answering sorts of questions and things. This is a graph that shows the concentration of carbon dioxide in the atmosphere. And you can see this graph starts in 2002 and continues on through 2014. What do you notice about this line? What kind of, what do you notice? I'm going to see if Kyla, is with us. Kyla was with Ms. Wood this morning, and obviously just in Blackboard. So this whole Zoom thing, I don't see her on the Zoom list unless there's hidden people. Is that the whole list, Mr. Ross? Or is there anyone kind of hidden there? Participants 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think she left Blackboard. No, she did. Well, that's sad. We'll get her in. We'll get her in. We'll get her in yet. All right. So carbon in the atmosphere. The line isn't straight. Why does the line go up and down? Or why? I'm not. This isn't like a global warming's happening sort of discussion. This is the actual concentration of carbon in the atmosphere. And it goes up and down, up and down, up and down, up and down, up and down. Why isn't it just a continuous straight line? Why does it go up and down? What would account for the ups and downs? If we look really closely, we'll figure this out yet. You can see between 2008 and 2010, we have sort of 2 years. So it goes up and then down and then up and then down. And Jesse, I think you've hit the nail on the head, Jesse. The seasons. How would the seasons account for an increase of carbon dioxide, then a decrease, an increase and a decrease? How would that work, do you think? The picture is blurry because of my Wi-Fi. Oh, sorry, Jonah. Yeah, Connor, you got it, exactly. Jesse and Connor, you guys are on it today. The seasons. So I did post a video at the very beginning of class. I just was hoping to get it into chat before everyone showed up so you guys could watch it now. Maybe some of you had a peek at it already. But the seasons. So in the fall, it's fall. So all the leaves fall, plants fall to the ground, and they start to decompose and break down. Plants are made of carbon. That carbon decomposes, it goes back into the atmosphere, and the amount of carbon in the winter gets bigger and bigger and bigger in our atmosphere. And then all of a sudden you kind of flip over to spring, and in the springtime, all of the plants start to grow again. And all of that carbon that was in the atmosphere all of a sudden kind of gets sucked out of the atmosphere and gets trapped in plants. And this cycle continues each year because in the northern hemisphere, I wonder if I have a map. The largest biome on Earth is in the northern hemisphere, and you can see the boreal forest kind of stretches all the way from North America all the way across into Asia and Russia. That boreal forest kind of loses, it stops growing in the winter, loses leaves, the deciduous forests, and then in the spring it starts to grow again. All that carbon exits the atmosphere. So what I want to do is I want to show you guys a little video. It's a pretty short one, but a good one, and I think it's 2 minutes long, but it does a really good job of describing how the nutrients, carbon, kind of gets released and then absorbed. So what I'm going to do is I'm going to go ahead and throw that link into chat. If you've already watched it, it's all good. If you would give me a green check when you're done, and just let me know when you're finished, and we'll just talk about it for a second, and we'll carry on. So it's 2 minutes. Come back, give me a green check when you're done. Thanks. All right. I only got 2 green check marks, so I'm not sure if everyone had a chance to watch the video. I'm just kind of interrupting the video now. How we doing? Obviously, we good? Just trying to give me a green check mark anyways. Just let me know you're kind of back if I'm interrupting your video. Green checks? Everyone, green check marks, please. Wait a second. That's better. There we go. So the video, I thought it was really cool the first time I saw it, and even the title, NASA satellite sees Earth breathe. It truly looks like Earth is breathing. The amount of carbon in the atmosphere increases, and then we get spring. Boom, the snow melts, plants start to grow, gets warmer in the northern hemisphere, that carbon just disappears. And then, you know, it just keeps going up and down every year. So when we look at the carbon cycle, we talk about how carbon enters and exits the atmosphere. Imagine if Earth went into something like an ice age, which, you know, is part of a natural set of processes and things like that. We'd get the big up from the carbon, you know, entering the ice age, and then we would never really get the down for, you know, maybe thousands of years. So it's amazing when you look at the concentrations, and normally graphs kind of over really, really long periods of time, you don't see the ups and downs, but in that video, it shows clearly every year the Earth is going big inhale, exhale. So that's why when you look at the carbon in the atmosphere at really short periods of time, like, you know, 10 years or so, you can see the ups and downs. But if you look long periods of time, it just kind of looks like a flat line. So I think it's important to recognize how Canada gets our energy. And we talk about the carbon cycle. It's important to talk about the kind of the human interactions in the carbon cycle. So obviously we live in British Columbia. The majority of BC's energy comes from hydroelectric. So, you know, we have dams all over the province, and those dams generate us electricity. You also know that BC has some alternative stuff. So, geez, when was it? It was in the summer, I believe. They installed some wind turbines up on the Penasque summit of the Okanagan Connector. Has anyone been up, driven to Vancouver recently and seen the wind turbines up at the top on the plateau, the Penasque summit? I haven't driven to Vancouver in a long time. It's been a couple years. This past weekend, did you see the turbines? Are they up there, Jesse? Are they, can you actually see them from the highway? Oh, cool, yeah. So obviously we're looking at alternative sorts of energy. I believe don't quote me on this, but I believe the turbines they installed provide power for almost 10,000 homes or something like that. It was a really big number of homes that those turbines can generate electricity for. So that's BC. You move over to Alberta, you get this big black bar. So Alberta burns a ton of coal, and look at gas, really big too. That's how they generate their electricity in Alberta. So Alberta doesn't have very many mountains. It's going to be difficult to build a dam in Alberta. You need mountains to build dams and reservoirs, things like that. Because it's so flat, it's tricky to build a dam to hold enough water to generate electricity, so they have to find other ways. So they've chosen to burn fossil fuels, essentially. Saskatchewan's a similar sort of looking map. Manitoba is nearly all hydroelectric. You get in Ontario, you get this big red bar. So Ontario has a lot of nuclear power generation. And same with Quebec, mainly hydroelectric, but they have a little bit of nuclear as well. And then the provinces on the very, very east coast are all kind of fairly small in terms of population and energy production, but pretty mixed out on the east coast. So that's how we get our energy. That's why it's kind of important that we have sort of renewable energy production so we don't release too much carbon. This is Canada over the last 40-something years, 72 to 2008. So the blue is oil. I know it's kind of this light blue is oil. So the amount of oil we're consuming kind of goes up and up and up to produce our energy. And then the green is gas. The dark blue at the top is hydroelectric, so it's been pretty consistent for the last 40 years, the hydroelectric. And then at the very top we have renewables, and the very bottom is coal. So coal is pretty low, but you can see this middle, these blue and this green, these together are oil and gas. we produce a lot of how we get our energy is burning oil and gas. And every time we burn oil and gas, we release carbon into the atmosphere. This is the United States, just for a quick comparison. And you can see the United States, about a third of their energy. They have 10 times the population of us in the United States. A third of their energy comes from coal, a little bit of nuclear, a little bit of renewables, and then natural gas is pretty big as well. So this is looking at from 2013 on projections. Obviously this will likely change, but just give you an idea. So talking about carbon, now this is going to match up with your notes from Unit 2 Learning Guide. Short-term carbon storage is found in aquatic and terrestrial organisms. So what that means is just plants and animals in the ocean and on land. Those are short-term storage. I will probably live, hopefully I live to like 80, 90, but in the history of the Earth, the billions of years that the Earth has existed and the billions of years it'll continue on for, my 100 years is not even like a blink. It's not even that long. So I'm a short-term carbon store. Something like a tree that lives, you know, maybe a couple hundred years. That's a bit of a longer-term store, but it's still really, really short in the sort of geological scale. Longer-term storage is found in the ocean, so the middle and the lower ocean. And basically when you get down to the bottoms of the ocean, you get, you know, all this carbon kind of gets layered up from these dead plants and animals, and it gets compressed and it gets turned into oil and gas over long periods of time. So oil and gas is just carbon. We are carbon. If we die and we layer the ocean floor, the pressure will build and build and build, and it'll crush our bodies into oil over thousands and thousands of years. So that's longer term storage. Layers of soil, decomposing organic matter become buried at the bottom of the ocean. And if you look at the bottom of the ocean, it's in layers. So you'll get, you know, a bunch of things will die, they'll form a layer, and then more things die and form a layer, and then more things die, form a layer. And those layers press as more and more stuff gets built up on top. It compresses what's underneath, and then you get that carbon, those dead things, you know, they get crushed over long periods of time. So long-term stores of carbon are things like oil and gas and rocks. Rocks are mainly made of carbon. And you might hear the word carbon store or carbon sink. Both kind of mean the same thing. They're interchangeable. So that's carbon. That's the carbon cycle. It's really important to revisit photosynthesis and cellular respiration at this point, because this is the basis for how carbon actually gets cycled. You know, you jump in your car, you drive, you burn some gas, that carbon gets released into the atmosphere. What happens to the carbon? Well, the plants absorb it. They turned it into a leaf or a nut or something like that. Then the squirrel eats the nut, the carbon's now in the squirrel. And then the, you know, the hawk eats the squirrel, and now the carbon's in the hawk. And then the hawk dies, decomposers eat it, it gets recycled. And this process just keeps going around and around and around and around and around and around and around forever. So carbon dioxide in the atmosphere plus water gives us sugar and oxygen. And then, of course, cellular respiration is this exact same formula, just flipped. So instead of starting with carbon dioxide and water, you're ending with carbon dioxide and water. And instead of ending with sugar and oxygen, you're starting with sugar and oxygen. So it is the exact same process flipped. So cellular respiration, exact same thing, reversed. You have your carbon dioxide and your water. It's what we take in. Sorry, carbon dioxide and water. Sugar and oxygen is what we take in. I breathe in the oxygen, I eat the sugar, and then I produce carbon dioxide. When I exhale, I produce some water, and I get that energy. So the energy we consume is for growth, repair, other life processes, doing things, moving, talking to you, doing my job. I need food to provide myself with that energy. So extremely important ideas: cellular respiration, carbon cycle. Decomposers are an important part of all of the cycles because they are what recycles the stuff back into the system. Imagine for a second, just for 1 second, imagine if everything that had ever lived on Earth never decomposed. We're talking about every plant, every animal, dinosaurs, whatever. Imagine if they would die and just lay there, and a plant would lose its leaves and those leaves would fall and just stay on the ground, and they didn't get recycled and decomposed. What would it look like outside? Would there be any carbon left in the atmosphere? No. All that carbon would be pulled out of the atmosphere from plants. The plants would grow and then die and fall over, and then there'd be no carbon left in our atmosphere at all. So the decomposers are an extremely important part of this process. If the nutrients, the carbon, doesn't get recycled back into the atmosphere through decomposers, then it would just get pulled all out of the atmosphere and there'd be nothing left. We'd all die. Be sad. There's also carbon exchanges in the oceans, and this is the major sort of carbon exchange on Earth, is in the oceans. So this is a really weird diagram because the equator's in the middle, and we have the North Pole over here and the South Pole here. So if you can imagine it rotated 90 degrees, it would probably make a little bit more sense. But anyways, you'll get the idea. So at the equator, we have really, really sunny days. And that causes the water to get warm, and warm water rises, and carbon dioxide is released. And then there's very low nutrients there, though. So you go back, this is the ocean surface. The carbon dioxide comes in at the poles, goes back down to the bottom of the ocean, gets cycled around, back to the equator, and gets released. Why is this important? Well, if you think about where the majority of kind of tropical plants and things like that are, in that tropical band where you have all these rainforests with really lush jungles, lots of plants, that's where all that carbon gets released. Those jungles absorb all the carbon, and the cycle continues, and it happens both in the south and the north hemispheres. So really low nutrient, low carbon water kind of floats along the surface, and then when it makes it to the pole, it gets really cold and dense, so all that carbon kind of falls back down, travels along the bottom of the ocean, gets released back to the equator. So it's another cycle that's happening underwater. Ocean mixing. Another huge, we take for granted this one, a huge release of carbon is in volcanic activity. So you can see the red line represents atmospheric carbon. Of course, we're looking over long periods of time, so we don't get the ups and downs from the seasons, but we're looking at 1960 and we're now up to 2020 almost. So it's almost 20 or 60 years-ish. You can see the atmospheric carbon's increasing. And you'll also see that you get these spikes when volcanic activity occurs. So when volcanoes erupt, they release massive amounts of carbon dioxide into the atmosphere, like massive amounts. Now, we have been in a relatively calm period of volcanic activity on a geological scale. In the last couple hundred years, there's been very few volcanoes that have erupted for long periods of time. But volcanoes can erupt for literally like 10, 20 years, releasing massive amounts of carbon dioxide in the atmosphere. So we've been relatively stable lately, but every once in a while it'll happen. So that can have another huge effect on atmospheric carbon levels. Forest fires are another big one. Gets dry in the summer, forests burn, all of that carbon that was stored in that tree is now back into the atmosphere. So that's why forest fires are a huge deal, and that's why climate change makes it warmer in the northern hemisphere, and when it gets warmer, we get drier, longer summers, it gets more chances of forest fires. If you've grown up in Kelowna, you've likely seen the impacts of the Okanagan Park Fire. We had the Fort McMurray Fire last summer in Alberta. the human impact is very large, but the impact on the environment is even bigger. So we'll just talk about finish up carbon here, and we'll call it a day. 2 more slides. So human impact. Many human activities can influence the carbon cycle. Since the start of the Industrial Revolution about 160 years ago, carbon dioxide levels have increased by about 30%, mainly due to burning fossil fuels. So fossil fuels, oil, gas, coal, anything that involves old dead stuff. In the previous 160,000 years, the increase was about 1 to 3%, and then in the last 100 years, it's gone up 150 years. Carbon is being removed from long-term storages, so burning fossil fuels takes the carbon out of the ground, puts it into the atmosphere, and there's no mechanism to counteract all that extra carbon we're putting into the atmosphere. There's nothing, no natural balance. It's not like the photosynthesis, cellular respiration balance between organisms. You end up just releasing a bunch of carbon. There's nothing to counteract it. CO2 is a greenhouse gas. You guys know that. Traps heat in the atmosphere. Clearing land for agriculture and urban development. We cut down the trees. Those trees are absorbing carbon. If we cut them down, then we don't have anything absorbing that carbon anymore. Those trees aren't absorbing it anymore. And farmland does not remove as much CO2 from the atmosphere as natural ecosystems do. So that's human impact on the carbon cycle. The last thing, you've likely seen a graph like this before, but this is the carbon cycle, or the atmospheric carbon levels for the last 400,000 years-ish. How do we get these numbers? Humans go back to, humans go back to about here, 150,000 years, but sorry, my line's different. Recorded time only goes so far. How do we get the numbers back past everything past, let's say, the last 150, 200 years? Nobody was really recording atmospheric carbon. So where do we get these numbers from? Obviously we have numbers, CO2 parts per million in the atmosphere. Anybody know how we get a number from 250,000 years ago? Where does that come from? We just make it up? I can tell you we didn't make it up. We recorded it. How? We've only had the ability to record CO2 in the atmosphere for the last, let's say, 100 to 200 years. So we're talking basically this to about, right here on this graph we can record. Everything back here, no recordings. How? How could we do it? Is it magic? Just have some magic? You make it up? You just guess. Well, I think it maybe was like about 240 parts per million. We're wizards. I wish I was a wizard. I could take some carbon out of the atmosphere with my wizardry. Can't do it. How do we do it? How do we figure it out? If we look back, how do we look back in time to figure out how much carbon? Nobody knows how we measure carbon 200,000 years ago. Surely somebody's seen a documentary somewhere that says, this is how we measure carbon 250,000 years in the past. Nobody. That is probably the most frightening thing I will ever encounter today, is that nobody in this whole class of very intelligent grade 10 students knows how we measured carbon 100, 200, 300, 400,000 years ago. Jeez. All right. Your homework is to finish Unit 1, climatograph, create a creature, learning guide, test. Those 4 things. Your homework is also to figure out how we can measure carbon in the atmosphere 200,000 years ago. I'm going to throw that on there as well. So I'm going to leave you guys there. We're going to start class on Thursday. Yeah, we're going to start class on Thursday with the answer to Mr. Borden's question, how do we measure carbon levels in the atmosphere when we weren't even humans, when we weren't here on this planet? How do we know? I believe somebody out there knows. They're just too shy to tell me. But anyways, tomorrow you guys have a class with Mrs. Ward. You have a big double block of socials, and then on Thursday we're back with science again. No field trip on Friday because of the professional development day. So there you go. I'll leave you with that. Have a good one, guys, and we'll see you on Thursday morning.